So torque is one of those ones, kind of like momentum, that has a really difficult definition because it's really just a mathematical product. But we can physically relate torque to forces that cause rotation. So the actual definition of torque is something along the lines of the product of a force and the component of the lever arm perpendicular to that force. Which cause rotation. Okay. About an axis. Okay, so one of the most important things that we have to have is we do have to have an axis of rotation. So what I'm going to do is I'm going to assume that the axis of rotation is the pivot point. So I need to identify the pivot point. Well, the pivot point is essentially going to be the center of this bolt, and my axis is actually going perpendicular through the page because the rotation has to be perpendicular to the axis. The rotation is perpendicular to the axis. So in this case, my axis is straight up out of the page, which means I can have a clockwise or a counterclockwise rotation in the plane of the page here. So what that means is that about this particular axis, I need to apply forces that will cause clockwise and counterclockwise rotations. Those forces will contribute to a torque. Now, the next thing we need to talk about is this idea of a lever arm, because this is a new definition. The lever arm is actually a vector. It is a vector that points from the axis of rotation to the point where the force is applied. So in order to define the lever arm, you have to actually know where your force is located. So I could apply forces anywhere along. So for example, if I applied a force at this point by putting my hand here so that I could turn this wrench, maybe I apply a force here, okay, and I apply a force in that location, or I apply a force closer to the end of the handle, okay, the lever arm would be measured to that point, directly to that point. So I would have, for this one, I would have a lever arm here. We do define the lever arm with the letter R, and we use R because it's kind of like a radius. So notice that it starts on the axis of rotation and then points there. The direction does matter for determining the direction of the torque, so we do have to keep that in mind. If I was using this force over here, my lever arm would be here. Alright, so those are my possible lever arms in this situation. So you can see that the further away I apply my force, the bigger the lever arm becomes. So that's part of like simple machines that you might have learned about in kind of middle school, that a lever provides you mechanical advantage because it makes it easier to do work using a lever with this kind of action. So in this case, the lever arm is going to make it possible to produce a larger torque. because it's going to be a product of the force and the lever arm. So the larger the lever arm, the larger the torque is going to be. Which is why generally when we use tools such as hammers and things, hammers involve rotation. We don't hold the handle really close, we hold it further back. Same with like holding a baseball bat. In general, if you want to have a larger kind of force, or you want your force to cause a larger change in momentum, say for the ball, when you're swinging baseball, you want to hold the bat further away and you want the ball to hit towards the end of the bat. But if you want to be able to swing that bat quickly, we don't want a really long lever arm, so that's when you might choke up on the bat. So it'll be you'll be able to get around quicker. So there's some advantage and disadvantage to having a long lever arm when it comes to rotation. So the lever arm here is good, but it's not enough, because it says here that we want the component of the lever arm that is perpendicular to the force that is applied. So these forces that are applied were actually perpendicular. Okay, so in this case, if I wanted to find the torque, I would just have to take the magnitude of this force and multiply it by the lever arm, because they're already perpendicular. But we don't always apply our forces directly perpendicular. It's better if we do, but sometimes maybe like if you're working on a pipe, you can't quite get that perpendicular handle on it. Maybe you actually apply that force at an angle. So if I press on this thing at an angle, maybe closer here towards the end, then in that case, it's not perpendicular. So what I'd have to do is I'd actually have to figure out the component that's perpendicular. So what I do is I would draw what we call an extended body diagram. And when we're dealing with torques, we don't draw free body diagrams. We draw extended body diagrams. So for most of what we're going to do over the next unit is we're going to draw extended body diagrams. So what you do is you draw the forces at the point they are applied. Okay, so you draw the forces at the point they are applied to the object. They do start on the object, just like with a free body diagram. And then they point away. So that way, when we draw our extended body diagram, the forces are drawn, so that way we can identify the lever arms for torque. So it's really important to actually draw the forces, which will allow us to identify our lever arms. So that's going to be part of our process when we solve problems involving torque. So if I wanted to draw an extended body diagram for this this guy here, then I don't want my force drawn like this, even though that's how it might look in the picture. I'm going to redraw my force so that way it is starting on my object where it is applied. And we'll talk more about where it's applied when we get to things like rolling and stuff, because it'll really matter where on the object. But for now, we can just draw it as generally where it's being applied. We're kind of assuming that this is a thin handle, so that the thickness of the handle doesn't particularly matter. So they might give you an angle for that force. So when this force is here, you know, they might have given you like this angle here, or they could give you this angle here, or if they really wanted to mess with your head, they could have given you like this angle here. So you do have to be careful, which is why I actually like this definition, because it tells us that it doesn't matter what angle they give us. What we have to do is we need to find the component of the force that is perpendicular to the lever arm. So if I make a right triangle with the force, this angle theta right here would give me perpendicular. If they give me this angle theta, then my perpendicular component here would be F sine theta. But if for some reason they had given us the angle over here, I'll call that one phi. Well, that didn't come out very well. If they had given me this angle phi instead, what I would have done is I would have resolved this triangle a little different, and I would have still found the perpendicular component, but my perpendicular component would have been the one over here. And if I given that one, that F perpendicular would be F cosine of the angle phi. Now, of course, if they give you an actual numeric angle, you would just have to, phi is just going to be 90 minus theta. So that isn't a big deal. You do have to be careful, because on the AP formula sheet, they're going to define torque as being based on sine theta. And it can be based on cosine theta, because it's not really the sign that matters. It's that you always want the component that's perpendicular to, between the lever arm and the force. So in this case, we actually didn't find the component of the lever arm that was perpendicular to the force. We found the component of the force that was perpendicular to the lever arm. If I had wanted to find the component of the lever arm that was perpendicular to the force, that actually would have been a little bit of a different process. And in this case, that would actually be the harder way to do it, the harder way to visualize it, because what you would have had to do is you would have had to make a right triangle with the force. So I would have had to come out here and made a right triangle. And then the lever arm here would be my hypotenuse. And then I would have had to have found, I would have had a right triangle here. So I would have a component here that's parallel to the force, and I would have had a component R perpendicular here that is perpendicular to the force. So you would have ended up having to figure out, well, what's this angle compared to what's theta and so forth. So that would have been a trickier process. So when we mathematically go to define torque, there's actually a couple different ways that you can find it. Now, the angle, the simple way to determine the angle if you are going to use sine. So if you do want to use sine theta, then that's where drawing in your lever arm really comes in handy. Because if I continue this lever arm axis out, and I actually draw in, okay, so let's make that darker. Let's draw in my lever arm here. So here's my lever arm R, okay? And so once again, let's say that my force is being applied here at that angle. Then if this is the angle theta and this is the angle phi, then you can always use sine theta sine of the angle between R and F. So you can always use sine of the angle between R and F to calculate torque, as long as you're always using the angle between R and F. So because if I take the sine of this angle and I take the sine of that angle, I am going to get the same value, okay? Because those angles are complementary to 180 degrees. So if I was given those, but if I was given this angle, so let's say I was given this angle right here, that angle is not the angle between R and F, so I cannot use sine. So I can use sine for this angle theta, I can use sine for this angle phi, but this angle alpha, I would not work. It would not give me the correct value. Now, I personally find it easier just to find the perpendicular component. So that's usually the way that I define it. But if you are going to use the sine, because you find it confusing to find the perpendicular component, you just want to always use the sine, then just make sure that the angle that you're using is always one directly between R and F. So it can either be theta or it can be phi, but not alpha. All right, so now that we've kind of talked about all of the different factors, let's look at the equation. So the equation for torque and the symbol for torque. Torque is given the Greek letter tau. So this is the Greek letter tau. It is actually a lowercase tau. Capital tau just looks like a T in Greek. It really just looks like a T. But this is the lowercase tau. You make it basically with a squiggly on top and then kind of like a J type thing please make sure that you're drawing towels and not T's. Okay, that is really important that you're using the appropriate symbol. So that's something that you should practice. I don't always make it super curly. Sometimes I'll make it a little flatter. And the big important thing is really that big J swoop and then coming into a capital T. Because obviously our lowercase t's look like this. So you need to make sure that your towels don't look like lowercase t's. You have to make sure they don't look like capital T's, which stand for period or temperature or things. You need to make sure that it is distinctly a towel. And that's one thing that I've learned from grading your papers is some of you need to pay attention when I tell you to write your letters properly, because sometimes I can't figure out what you're writing. And if I can't figure out what you're writing, you can't earn points. So please pay attention to your handwriting. Handwriting does matter in physics because you're representing physical concepts with equations. Okay, so torque is the Greek letter tau, and tau is R perpendicular times F, or F perpendicular times R. So that's what this says. It's the product of the force of the component and the lever arm that are perpendicular to that force. So that's what this one says. But these two are equivalent statements. So you can do R perpendicular F or F perpendicular R, just as long as these two are perpendicular to each other. So you can either find the component of the lever arm that's perpendicular to the force, or you can find the component of the force that is perpendicular to the lever arm. Either of those will work. So then, once you have that, the other way you'll see it written on the formula sheet is you'll sometimes see an RF sine theta, or you might see an FR sine theta on the AP formula sheet. And this is assuming, this theta is assuming that you are using the angle between R and F. So if you're going to use this definition, one of these two definitions, these are the same because the order doesn't actually matter, then that will give you the angle between R and F, will give you the ability to use sine. So those are kind of the mathematical definitions. Now if we look at this, we're just taking lever arm, which is a distance, and force, which is newtons. So the unit of torque is going to be the Newton meter. Work also had a unit of Newton meter, but work we can also rewrite as joules, because work and energy are interchangeable. Work is the change in energy. So a Newton meter and a joule are the same thing for work and energy, but you cannot use a joule. This does not equal the joule. You cannot use joules in place of Newton meters here, because in this case, torque is not equivalent to energy in any way, shape, or form. All right, so the next thing to realize about torque is that torque is a vector. So we have to use a right-hand rule to determine the direction. Now, the actual direction of torque is not as important as the direction of rotation. So the direction of the torque vector is not the same as the direction of the rotation. And there's a lot of vector calculus that goes into this. So it's not so important for you right now to know why. That is, if you're interested, you can ask, but it's not important because the sign is what we usually need to know, whether it's going to be a positive or a negative torque. Because if we're going to add up torques, we need to figure out whether the torques are positive and negative and add all the positives together, subtract all the negatives, kind of like when we're doing net force. So the direction of this vector does actually matter. So how do you determine the direction of the torque vector? So to determine the direction of the torque vector, so say we've got this situation, let's say we're applying my force here at this same point, and let's say we have our lever arm here. Okay, so we have our lever arm vector. So the way this works, and it's a little tricky, there's different ways, if you look it up online, there's different ways to do this, but I'll show you a little bit of a shortcut. So if I put my fingers, point my fingers in the direction of the first force, first vector, point fingers in direction of the lever arm vector. That's why the R is actually written first, starting at the axis of rotation. So that's the first step. So I can point my fingers anywhere in any direction as long as they point essentially away. So I pretend kind of like the heel of my hand, and I put that kind of at the axis of rotation. So I'm pointing my fingers in the direction of the R vector. The next thing you do is you rotate your hand so that palm faces the force vector. So if I'm here, I'm going to have to rotate my palm so that it faces the force vector. So my palm here is pointed at that force vector. Now you want it to do that over the shortest rotation. Because technically I could do this like this, and I could keep rotating, and that would be silly. Okay, so just whatever you need to do to rotate it so over its shortest so it's there. So my palm's going to be facing there. You don't want to get your arm all twisted. Sometimes that gets a little bit tricky. So you should be trying this with me so you can figure that out. Okay, so palm, fingers pointing away, palm rotates to face the force. And then all you have to do is curl your fingers, and then your torque vector points in the direction of your thumb. So you curl fingers, and then your torque vector points in the same direction as your thumb. So fingers in the direction of R, rotate the palm so it faces the force, curl fingers, so this torque vector points up. So basically the torque being caused at this point is up. We call that out of the page. So the torque vector points out of the page due to that particular force. So out of the page is considered a positive value. Into the page would be a negative value. So let's say I had a different force, and let's say that I was applying that force here. Okay? So that this was F1, so torque 1, this is F2. So F2 was being applied there. I would need to have a vector for its lever arm, which would be that vector there. So this would be R2, this would be R1. So if I wanted to find the direction of this one, I would put my fingers in the direction of R2. I would rotate my palm so it's in the direction of the force. And then when I curl my fingers, my thumb is pointing into the page. So I use an X to represent into the page. I used a dot to represent out of the page. And into the page is a negative torque. Now, where do these dots and crosses come from? Well, if you picture an arrow with fletching, if I was to look at the tip of the arrow dead on, I would see a point. If I was to flip that arrow upside down, I would see the fletching, which would make an X-ish. So when I'm looking at the tip of the arrow, when the tip of the arrow points up into my eye, in this case up into the camera, that is looking at the tip of the arrow, so that's a point. If I rotate it downwards, then the tip of my arrow is pointing down, so I'm actually looking up at the fletching. So that's where the X comes in. So out of the page is positive, into the page is negative. Those are the most common directions, although they can be in any other direction. But generally, since we're drawing forces in 2 dimensions, our torques are going to then be out of the page or into the page for that. Now, there is a shortcut, and that's because positive torques always cause counterclockwise rotations. Positive torques cause counterclockwise rotations. So if I were to look here and I were to try and curl my fingers counterclockwise, my thumb points out of the page. So that's kind of the shortcut. If I know the direction of the rotation that torque is causing, and if I think about it, if I push down on this wrench in this plane, that's going to cause this wrench to move in the counterclockwise direction. So if I know that, then I can just curl my fingers counterclockwise, and then my thumb tells me, oh, well, my torque then has to be out of the page. If I look over here at this one, by pushing this kind of up, what that's going to do is that's going to cause us to rotate in the opposite direction. So negative torques cause clockwise rotations. So that's the shortcut. So then if I wanted to figure out the direction of this torque, well, I rotate my fingers clockwise. And if I curl my fingers clockwise, my thumb points into the page. So that's the same thing that you happen by using this right hand rule. You can actually cheat and use the direction of the rotations to determine whether the torque is clockwise or counterclockwise. Now this is going to matter because if you have several different torques, you need to find a net torque. So our net torque is either the net torque like this, or you can write it as torque net. Either way, it is the vector sum of all of the torques. So just like you could write a net force equation, you can write a net torque equation. So we can actually do that for this guy. If these are the only two forces acting, if I wanted to find the net torque, then generally what I do is I write all of the magnitudes of the torques that are counterclockwise, because those are positive, and then I subtract essentially the sum of all the torques that are clockwise. And then by doing this with the negative, then these are just the magnitudes. And then these are just the magnitudes. So then I only have to account for one negative. Or you can do that the torque net is equal to the sum of all the counterclockwise torques plus the sum of all of the clockwise torques. And in this case, because you're using a plus sign here, you would have to make sure that you add the negatives onto each torque. So it doesn't matter, just as long as you don't forget the negatives and you apply the negatives only to where they apply. So your net torque can be calculated with the sum of the different torques, whether they're counterclockwise or clockwise, matters for direction, kind of like upwards and downward forces matter. So you'll do the net torque equations very similar to what we did here. So if I was to do either of these methods, then what I would end up with my net torque in this case, I'd look at my counterclockwise torques. Well, my counterclockwise torques are this one, so that would be torque 1. And then my clockwise one is going to be torque 2. Now I'm using the method where these are magnitudes, because that's the way that I usually do that. So then the magnitude of this one and magnitude of this one. Now I need to make sure that at the end when I go and calculate that I don't just leave my vectors as positive or negative if I know my directions. Indicating that it's positive or negative is good, but out of the page into the page is better. Also indicating the direction of rotation will help. We'll look at that when we get to problems. So then my net torque here, in this case torque 1 minus torque 2. So let's say I had an angle here. So torque 1 would be R1 times F1 sine theta. It's sine because this theta here is the angle between R and F, so the perpendicular component to the lever arm for the force would be based on sine. And then torque 2, I do this as a 90-degree angle, so this one is just going to be R2 times F2. And then the magnitudes of those forces and would need to matter, because if they're the same magnitude of forces, then it would matter where these distances are. But if F1 is bigger anyways, and you got your angle and so forth, you'd have to figure out, so is this net positive? Is the result of this causing a counterclockwise rotation? So is this wrench going to go counterclockwise, or is the torque due to F2 bigger and this is actually going to rotate clockwise. You'd be able to determine that by the sign of this sum when you actually go to plug in numbers. So there you have it. That is torque.